load now. Yes. So I'm doing number 6 on Newton's 3 laws here, as a little bit of a revision. So in number 6, you have a rubber ball, and it's 0.2 kilograms, and it's dropped from a height h, and it falls from rest onto smooth concrete floor. It hits the floor at speed 7.8. So what happens is it falls, and then it hits here at 7.8 meters per second. And then what happens is it bounces back up, and it goes to a height of 2.4 meters. Sorry. So the first question is, what's the h? Okay. So we have u equals 0, v equals 7.8, a equals 9.8, t equals, we don't know, s equals, that's what we want. So what formula? V squared maybe? V squared equals u squared plus 2as. So 7.8 squared equals 9.81. So that's 2 times 9.81 times s, which is h. Okay, what's the h here? 7.8 squared over 2 times 9.81. What's that, please? Or do I have the answers to that? Is it 3.1? Yeah? It's 3.1, yeah. Is that what you got in the calculator? Yeah? Okay. Now the second part is they want the speed here. Look, they want the speed here. So, u, we don't know. Do we? No, is u 7.8? No, it's not. U, we don't know. So that 7.8 is the speed when it hits the ground. And we want the speed when it leaves the ground. So we don't know this speed. V is 0 because we're going to look from here to here. A is minus 9.81. S is 2.5. Okay, what formula shall I use here to get? The same one, isn't it? Yeah, same again. V squared equals u squared plus 2as. So that means the u is square root, that would be 5 times 9.81. What's that, please? It's about 7, is it? Oh, it is 7, yes, 7, roughly 7.
Yeah, so.
Okay. Next part is the impulse, which is the change in momentum, which is mv minus mu, which is 0.2 times 7 minus 0.2 times minus 7.8. And in this picture I'm saying down is minus and up is plus here. So what number do you get here? 2.96.
Yes.
Exciting. Right, kilogram meters per second. And lastly, when the ball hits the ground, there's a force that pushes the ball back up. And they want this force. So what formula should I use there? I should use I equals Ft. So I get now F equals I, well, I should really say delta T, the small time. Delta T, well, you know what? I won't write it as I'd like to write it as delta P. Delta P over delta T, this is the other way to think about it, is F. So F is delta P multiplied What am I doing? I'm so tired. F is delta P over delta T. So that is 2.96 over, and in the question they say it is 33 milliseconds minus 3. So what's that? 89.6. You rounded it up? Okay. Okay. Is that okay for you, Louise? Yeah? So let me see your picture. Yeah, so much more difficult, isn't it? Now, I know why you drew this, because the question didn't make it clear that it's straight down, but if we go to have a highlighter. No. The only thing, they really should use the word, you see here, vertical. Because vertical means like this. Straight, yeah. And I can see when I read this, they don't really use them until actually the question. Unfortunately. But the word dropped in English, it usually means vertical. Dropped. So I suppose this is the clue, this word here, dropped. Because dropped usually means like that. Yeah. I don't like when English is the problem with the question because I feel like it's not your fault, you know. And, you know, dropped. Maybe some people know this is dropped, and maybe some people don't know this verb. Yeah. What are you know dropped? Yeah. Do we know other verbs like dropped? What else could you have? So, if I do this, throw. But there's another verb as well. Oh yeah. Yeah, think. Yeah. Go ahead, release. Release is good. For me, release kind of sounds like dropped. And what about this one? Flung. Yes. Flung is one, yes. So we have throw, flung, flung. Anything else? No? Projected. Like projectile, yeah. Projected. It's like projector. So not the same thing. Projected. And now we were talking about dropped, released. Anything else? Let go. Let go. Anything else? Don't think so. No. And then let's not forget, if it was on the table, we have these verbs. What's that? Push. Give me more. Well, okay, forward. What else? Push. Tunked. Hit. Moved. Shifted. Anything else? Nudge. Yeah. So there's many verbs here, okay? So that's why it's important, you know, if there are new words, to highlight them, so you can remember them, okay? Well, we'll start the next topic now. Okay. So, work. So, what's work? I mean, you know what it is in English, so what does it mean? Work. Just give me English definition, yeah. Now give me like a simple meaning of work. You know, you usually mean, you know, to do something, yeah. Yeah, so work, we'll talk about energy as well. So when we talk about work, okay, we always should picture somebody or something, and maybe they're doing something. I don't know. Maybe they're like me. Maybe they're using a laptop, you know, or maybe it's a person and they're moving a box, or maybe even just person walking up a hill. This is all example. battery. These are all examples of work. And the key thing that's in common with all of these is that there's some kind of force that's being used to do the job. Okay? So first thing you need to note is when you have work, that means there's some force present. Okay. I can actually use this or this. Okay, so now we can talk more about the physics definition more precisely. Well, does anyone know it? I think you had it, Abraham. What were you saying? Yeah, so work definition, work done, which we use as letter W, is the amount has two M's, doesn't it? Or one? Amount, yes. Work done is the amount of energy, well, why don't you tell us, Abraham? What are you saying? Work done is to do a job, isn't it? Yeah. The amount of Yeah, well, we're just trying to get the idea simple first, and then we'll make it more precise. Okay. Work done is the amount of energy. What verb would I like? No, let's forget that. Yeah, let's forget that. No, forget that. Forget it. Alright, we'll take a different approach. We'll go straight to the physics definition. Okay, so what you have here, this is 1 kilogram, and this here, well, I guess it doesn't have to be 1 kilogram. 1 Newton is pushing this. We picture a man pushing this, so it moves 1 Newton, and it moves 1 meter in total. Okay, so in this example, we say the man has done work. And we measure work done in, what's the unit? What's the unit for work? Do you know it? Joules, yeah. We measure work done in joules. And this is the definition. 1 joule of work equals 1 Newton applied to a mass to move it 1 meter. So that's 1 joule of work. If you use 1 Newton of force to move something 1 meter, that's 1 joule of work. So for example, here, okay, actually I wrote 1 kilo, but the mass isn't important actually, so forget about the 1 kilo. If I push this, look, I'm doing work, okay? Let's say my force is 1 Newton, so if I push this with 1 Newton force, 5 meters, how much work have I done? 5 joules. Okay, so you can see that 1 joule, that can move something 1 meter. So it makes it feel like it's very big. Okay? Right. So can we have a formula here for work? And we can. I should also point out that the force direction must equal the displacement direction or the velocity direction. Sorry about that, it's not clear. But if I go back to my picture, the force is here and the movement is here. So for my definition, they must be the same direction, okay? He must push this way and it must move this way.
So the turn oil is 7 Newton.
Say that again?
Turn is 7 Newton temperature.
No, well, it's not the same, but very similar. And I'll give you the formula now. The work is the force, which is what you're saying, multiplied by the distance. So for example, if I have this box here and I use 10 newtons and I move it 20 meters, how much work have I done? 200 joules of work is what I did. Yeah. So we're clear on what work is, yeah? Now, work isn't everything, there's more to it than just that. But let's do a very, very small example here. So, let's see, okay. So let's say this is 2 meters, and I have a box here, and the box is 5 kilograms, and, well, let's draw the person bigger. Yes, person. And they're lifting this box, and they're lifting it up here. There's a force down here. It's weight. Do you remember what the formula is for the weight force? Yeah, weight equals m multiplied g. So let's make it 10 kilograms so it's easier for me to do. 10 kilograms. So this here would be 10 multiplied 9.81, so that's 98.1 newtons down. So if the man wants to lift it, how much force must he give it in the up direction? Yeah, at least 98.1 newtons. So his force is equal to 98.1 newtons if he wants to move it. How far does he move it? 2 meters. So in this example here, the work done is 98.1 multiplied 2, which is, what's that, roughly 196.2 newtons. Not newtons, sorry. Joules. That's how much work he's done. So you can see, if you want to lift something, it's a lot more work done than pushing something. Okay. Now I have a question for you. Can I scroll down? Yes? Yep? No? I can go down? Yes? Okay. So here, we have a hill. And here we have 5 kilograms again. And I move, the man, oops, where's it gone? Here's the man. And he moves it up to here. Like that. Okay, and then let's say we have, oh I don't know, a little ant or something. You know, little ant, little insect. And the ant takes 1 gram. And the ant takes the 1 gram up here. And then the ant jumps down, goes around, and then takes another gram. And so on. So this will take a very long time to do. And who does more work, the man or the ant? The ant? Because, yes? Yeah, the distance, isn't it? Yeah? The answer is they both do the same work. And if you want to see the reason why, go back to this example. Let's pretend instead of 10 kilograms it was 1 kilogram. How much work do I do if it's 1 kilogram? Can you tell me? If it's 1 kilogram, not 10 kilograms, how much work do I do? What's the only difference? Yeah, instead of 98.1, what would it be? No, it'd be 9.81. So instead of being 98, it'll be 9.81. So what would the answer be? 19.62. So if I did this 10 times, what's my total? It's the same. See? So this is what I'm saying, that the work done is the same. But there is something that is different between the ant and the man. And that's our next idea, which is called power. And power is how much work is done divided by the time. So the man has more power because he can do the work quicker than the ant. Okay, so let's say it takes the man 10 seconds to do this, and let's say it takes the ant, I don't know, much more than 100 seconds. Let's say 10,000 seconds, 100,000 seconds maybe. So in the formula, the work is the same, but the time is different. Let's make this here, what was my last example? 2 meters. Okay. Let's make this 2 meters as well. So, sorry, I'll draw this again. So the man lifts this up 2 meters, and it's 5. And then the ant does the same thing, but the ant does it piece by piece, so it's much slower, but it's still 5 kilograms. So let's get the power. For the man, it will be 196.2 divided by 10. And for the ant, it would be 196.2 divided by 10, what did I go for? 100,000, didn't I? 100,000. So you see how different they are. I haven't talked about the unit yet, but you can tell me what the unit is. If it's work over time, what's the unit here? Joules per second. Joules per second. Okay. So what's it for the man, please? It's 19.62 joules per second. And then for the ant, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Joules per second. But there is a different name for joules per second. When we have 1 joule per second for power, we actually call that a watt. I don't know if that was supposed to be a joke or watt. Oh no, it's like a TV sketch or something now. Who? What? Okay, so we say 1 watt if it's 1 joule per second. And in fact, maybe you've seen this unit before. So has anybody ever bought a light bulb? And it says the power of the light bulb. What's the power of the light bulb? Maybe 100 watts or 60 watts. You've all bought light bulbs, yes? Yes, good. So for your bedroom, for example, what power light bulb do you have? Do you know? What is it then? 5. Now you could have 5. Is it an expensive light bulb or cheap light bulb? Oh, then I don't think it's 5 then. Maybe 50. 50, yeah. Anyone else know? For your bedroom? So bright. 100. It's very bright, yeah? Yeah. What about for you, do you know? 20? Alright. And you? Do you know? You don't know. Well, when you buy a light bulb, you'll know. So you have on different things at home the power. So does anyone know anything else in their house, the power of it? So we know light bulbs maybe. Would anyone know, for example, their TV or anything like this, their computer? Do you know that? I think I might, like here, if I look at mine. No, I think it's on the inside. I think this here would be about 25 watts. which means every second how much work is being done. 25 joules. Yeah? What do you think is the most power in your house? Most power? None, Michael, if not. Any idea? Most power? Almost. Certain. Not. Yeah. Produces heat, yeah.
Not oven,
No, something more than an oven. Huh?
The cooker.
No more, something more than a cooker. Electric shower.
Yes.
Electric shower. It's most power. Electric shower is like 9,000 watts.
4 seconds.
Yeah, 9,000 watts, so 9,000 joules per second is an electric shower. Now think about that, compare that with the light bulb. Light bulb is 60 joules per second. The shower is 9,000. So it's a big difference, okay? So power is very important. It's much more than just the work done. So we'll look at some more examples now. Or do I want to say... Yes, I'll just say one other thing about power and then I'll do some more examples. Can I scroll down here? Yeah. Okay. So we picture this is a car, okay, and this is a force that makes the car go forward. But we also know, or maybe you don't, there's a force going backwards as well that tries to slow the car down. What force is trying to do this? Yeah, but give me like the particular. Air, isn't it? Like if you're in a car that's going very fast, or you're on a bus or whatever, you feel all the air. And this is a force the other way, trying to slow you down. So this is force forward, and then this is force backwards. I'll call this one 1 and 2. So if this one is bigger than this one, of course the car moves forward. But what happens if they're equal? No, it doesn't.
Just an accelerator.
Yeah, if they're equal, there's no force. And if there's no force, what does Newton's first law say? Yeah, Newton's first law says no force. That means you have at rest, which is what you said, Abraham, or, what's the or? Constant velocity, yes. So in the example of the car, which do you think it is normally? It's constant velocity, okay? So this is what happens in your car. When you put your foot down, you go forward. But as you go faster, you get more force going backwards. And then the two balance. And then it's constant velocity. Does anyone know the names of these forces? The one that makes you go forward. This is called the drive force. And this one here? Don't know this word? No? This is called the drag force. New words? Okay. So let's write them down. Drive and drag. Okay. Can I scroll down? Yeah? Okay. So I'm going to do some examples. No, I'll say one more thing about this and then I'll do some more examples. So we have our car and we have our engine. So we'll put the engine in the front, and the engine is making the car go forward. So the work done is the force by the distance. Okay, but sorry, that's not. What's the formula for power? Work over time. So this means that work equals power multiplied time. Let me put that back into this formula. So I get power multiplied time equals force multiplied distance. Now let me divide here by time. Whoops. What's distance divided by time? Distance divided by time. Speed. Velocity, yeah. So now you have power equals force multiplied velocity. So you have force equals power over velocity, or power equals force multiplied velocity. So if I give you the power of the engine, then that means you can tell me what the force is. And the opposite. If you know the force, then you can know what the power is. Okay, now we'll do some examples. So I can do some examples now, yeah? Okay, so my first example, very easy to get us started. We have this box and we pull the box 30 meters and we use 80 newtons to do it. What's the work done? It's 80 multiply 30, which is 240 joules.
2000.
I forgot a zero. Okay. Now, let's say, for example, if the time to do this took 1 minute, what's the power? The power is the work divided by the time. So that is 2,400 divided by 60. What's that, please? 640, is it? 40 watts. Okay, now we're going to talk a little bit about angles. Okay, scroll down. Okay, so let's see, another example. Right, so we have here the ground again, and then what we have is a force here. Okay. And we pull it, but this time we pull it at an angle, and let's just say the angle is, I don't know, 40 degrees. Now this is quite different, because the problem here is the box moves to the right, doesn't it? But the force is not to the right. So what we have to do to fix this is we have to break it into the two pieces here and here. Oh, I should tell you what the force is, sorry. Let's say it is 150 newtons. Okay, so on your calculator, can you give me 150 cos 40, and then here is 150 sine 40. Okay, can you give me these numbers, please? What's this one here? The Cox one.
114.9.
And then the other one?
96.42.
96.42. Okay. Now, I haven't drawn all my forces on my picture yet because there's a force going down here. What force is that? mg. And let's not forget, and some people know this and some don't, there must be a force going up from the table called or. Now this might be new for some people, so I'll just explain that here. If you look at this, okay, it's not moving. It's not moving, right? There's a force going down, which is the weight, but because it's not moving, there must be a force going up. And there is. The table is pushing up. That's what that or is. It's called reaction. It's the up force from the table to cancel the mg. So there must be 0 then, yeah. So we get here, I'll write it down here, or plus 96.42 must equal mg. Now why did I add these together? Why did I add them? Why did I do or plus 96.42? Yeah, there are two forces going up. One from the table and then one from the rope. There's two going up. Okay. But that's fine. I don't care about this. Why don't I care about this? Yeah, I mean, all I really care about is this one. Why do I only care about this one? That's the way it's moving, isn't it? So I'm not very sorry, but I'm a little sorry. I didn't need to show you this. Okay? So anyway, work is force multiplied distance, which will be 114.9 multiplied, did I tell you the distance? No, we'll say it moves, 10 meters. So that is 1149 joules. Okay? Now, if this took, let's say 30 seconds, what's the power? Power is the work done over the time, which is 1149 divided by 30. Can you tell me this, please? What is it? 38.3 watts. Okay. Can I go down? Yeah. Okay, so next example now. One more example, then I'll let you try some. Okay, so now here we have a car that's going up a hill, and we don't know this force here, but I tell you the force pulling it back, I'll say it is 100,000 newtons pulling it back. You know this. Does anybody cycle? So when you cycle up the hill, you feel the drag. Now, I'll also tell you that it's moving at a constant speed of, we'll make it 10 meters per second. And we'll say its mass is 100 kilograms. Oh, sorry, you don't really need to know the mass. Oh, I forget about the mass. Well, keep it if you want. So we'll say the mass is 100. Okay, so what I would like to know is the force. Well, no, that's too easy. Or is it? No, the power. Let's get the power of the engine. What do I know about F? Yeah, why is it equal to 100,000? Because of the constant speed. We have another formula for force. What is it? Yeah. It's P over V, isn't it? Isn't that what I gave you? Now, we know the V. What's the V? 10. So if I bring the 10 up here, it makes another 0. So the power equals 10 to the 6 watts. Does anybody remember what we call 10 to the 6? What is it? Yes? Not giga? Not giga? That's too big. What's before giga? Mega. 1 megawatt of power. Okay. I want to show you something with this, another way to think about this, maybe. Yeah. No, I won't do that yet. Don't overload you. Little steps. Okay, anything else you need to see here? Well, I'll do it for fun. I like doing it. Okay. You know, in Ireland, Hong Kong, China, everywhere, what units do we use? We use meters, kilograms, kilometers. What are the names for this unit? What's its name? It's called the SI unit. Remember we did this in the first lesson. Although some places use the older system. Yes, it's not called metric, but what's it called? Well, it doesn't matter about its name. It uses the older system in units. Do you know which country uses the older system? USA. Yeah. So in USA they don't use joules. Does anyone know what they use for energy? No? Don't know? No, okay, I'll tell you. They use something called, you do know this, calorie. You know this word? Yeah. So, 1 joule, sorry, got that the wrong way. 1 calorie equals 4.2 joules. Does anyone have any food on them? Chocolate bar, anything? Any food? Coke? Anything that you bought from the shop. Do you have it on you? Bag of crisps? Nothing? Chocolate bar? No, I won't say that. Oh yes, this might do. So if I look here, if I can see, it says per 7 polos is 42 calories. 7 polos. How many did you eat? Maybe about 7? Only 2. I shared them, alright, okay. Well, if we say you eat 7, that's 42 calories. 42 calories. Yeah, so 42 calories, that's nice. That, oh no, it's not. 42 calories. How many joules is that? Well, multiply 4.2 by 42, what do you get? So 7 polo sweets equals how much?
176.4.
So roughly 176 joules. Which means when you eat 7 polo sweets, you can push 1 Newton of force 176 meters. That's how much work you can do when you eat this. Yeah? And this kind of surprises people because it seems like that's a lot or very little, doesn't it? So, you know, if you want to lose weight, exercise is a very bad way to do it because you have to do lots and lots and lots of exercise to use all the energy, you know. So if you really want to lose weight, the best way is to eat less, not do more. You get what I'm saying? Yeah. Now, does anybody know how many calories you should have per day? For man, woman, I don't mind. But woman is 2,000 about, and man is about, yeah. But there'll be a height thing as well. So we'll just say 2,000 calories. And what's the time? 24 hours. So we can work out the power of a person. It will be 2,000 calories divided by 24 hours. Now, please take care. There's a very common mistake here with food. When you say we need 2,000 calories per day, that's actually not true. we need 2,000 kilocalories, but nobody pronounces the K when they say it. That's 1,000 times more, isn't it? So can we get this in joules? How many joules is that? It'd be 2,000 times 1,000 times 4.2 all over 60 times 60 times 24, which is roughly 100. What is it, please?
27.
So about 100. So if I bring this now back to the start of the lesson, I was saying that when we do work, you know, like you lift a box, you write, whatever, there's always force. Yeah? And we think about the lights and the shower and the cooker and all this different types of things. But a person is also like a machine. So if we are like a machine, we are like a machine that is power 100 watts. So, what power is your light bulb is 100 watts. So you must think of you like a light bulb. You have, when you see the light bulb in your bedroom, you have the same power as that light bulb. Does that make you feel like a lot or a little? Do you feel like that's big or small? Yeah, I guess it's okay, 100 watts. It's okay, isn't it? So that's how much power people have. They are 100 watt machines. Yeah. Now, just to put you some more numbers in context, okay? A light bulb 100 watts, shower 7,000 watts, TV 100 watts, radio 2 watts. What else do we have? Hairdryer 2,000 watts, electric kettle 2,000 watts, electric heater, you know, on the wall, electric heater 3,000 watts. What else do we have in the house? What else is there?
Air conditioning.
Air conditioning is a lot. Air conditioning is probably like 4,000 watts. It's a lot. Oven is about 6,000 or 7,000. It's not quite as much as an electric shower. What else? Anything else? Kettle is about 3,000.
Working machine.
Huh?
Working.
Which?
Working machine.
The kettle?
No, the working.
Vacuum.
Oh, vacuum! Oh yes, vacuum. Vacuum is about 2,500. 2,500. Now there's a simple way to know what uses a lot and what uses a little. If it gets hot, it's a lot. Hairdryer, kettle, cooker, and even the vacuum cleaner. You want vacuum at home, right? So when you finish vacuum, the vacuum cleaner feels hot, doesn't it?
Yeah.
Yeah. So it uses a lot of power. Okay? So, I'll give you some questions to try now. Now, some of them are difficult, but try your best, okay? I'll let you work on these for a few minutes. Number 13 looks very difficult, so you can try it. These may look very familiar to you.
Yeah, I think we got some there. We got some fish.
Yep.